Hello everyone. Today we'll be discussing using Quadrotor Aircraft in open pit mining applications. My name is Mohammed Iskandarani and this is in partial fulfillment of the Mine 853 project. I hope that you'll enjoy today's presentation, and if there are any questions, don't hesitate to include them in your peer review evaluation. We'll look at first the outline for today's presentation. We'll discuss UAV background, so using unmanned aerial vehicles. The motivation, so how this fits within the mining sector. We'll look at a problem formulation where we'll discuss all the different tests and the solutions that we've included in the experiment. I find also for experimental setup it's important to include this in the actual presentation so that the viewers can really appreciate how the results were found. Now, at the end, we'll discuss the details of the results, and we'll conclude with some final remarks. And I'll give you a heads up in order to see some extra videos that I've made for this project. So let's start discussing unmanned aerial vehicles themselves. So what are UAVs? The definition we actually use for this is an aircraft without a human pilot on board. It's either controlled autonomously or by a human pilot on the ground. Now, the key word I want to highlight here is autonomous. Throughout the experiments in this project and the presentation, the UAV will be accomplishing the task by itself. So the user will only give a go signal for safety, and everything else will be accomplished in a decision-making process by the UAV. For those of you that have a piloting career, just understand that the use of complex control systems and autonomous flight with UAVs is actually replacing that career. So it's always important to understand these advantages. Other advantages are flexibility in autonomous flight, ability to accomplish complex tasks, and it saves time and human resources. I can always send one UAV or a team of UAVs to accomplish a task and in dangerous areas. So human beings don't have to be exposed to any hazardous materials, and we don't have to injure anyone. So this is quite important for big corporations that are using UAVs in order to prevent lawsuits and, of course, loss of human life. Other advantages that I would like to highlight are adjust UAV flight priorities. So the UAV is capable of doing this depending on the changing environment. There's also capability to handle complex weather patterns. So we can say sandstorms or something like that. It's able to adjust or even return to home base if it's too dangerous. We also have the ability for cooperative accomplishment of a task. As I mentioned before, we can send a team of these UAVs in order to accomplish the task. There's also a number of sensors that are included on the vehicle. So we see here a camera, but there could be other mapping equipment that is also available on board the vehicle. So I included this picture to show the complexity of these systems and how they all fit together. So let's look at the types of UAVs. So we have mainly the ones that are exploited the most are fixed wing and rotorcraft. Now, fixed wing are used more for long endurance flights, such as surveillance missions that are lasting for months on end. So you use the fixed wing type for that. On the other hand, the rotorcraft is a lot smaller than the fixed wing. It's more agile and flexible. This is mainly used for mapping rooms. For example, in military applications, you can send one of these things inside the building in order to map it or even engage the enemy. And it's always easier to explain how you lost a UAV than to explain how you lost a human being. So this is again another advantage of using these things. Now, for the purpose of this presentation and this experiment, what we'll be using is an actual rotorcraft called the Q-Ball X4, the details of which we'll be discussing further on in this presentation. Before this, we'll just look at some general applications. So why UAVs and how they're used in their daily life? If we look first of all at search and rescue, we can send one of these UAVs to either follow actual GPS coordinates that are pre-programmed or even use its infrared camera to locate the lost individuals. We can look at crime scene investigation. Now, in this case, what we have is there's no tampering of the actual crime, so no investigators need to be there. this is mainly used for, UAVs are mainly used for big crime scenes, and because they'll just hover, take important pictures, and then there is no tampering of the actual crime scene. Now, if we look at the next application, which is surveillance, we have military or civilian applications. In military, it's quite obvious. You send it around the enemy line, then you can observe what's happening. While for civilian, it could be used for traffic, so observing the 401 as an example. We also have hazardous area exploration. Now here, we can see that we want to prevent humans from being harmed. So examples of this could be fallout areas or even floods. So we send the UAV in order to inspect and maybe even bring this information back to the engineers in order to organize maybe a cleanup strategy of some sort. So these again are the applications that we used. Now, we want to be able to take the flexibility, autonomous operation, and efficiency of these vehicles I've highlighted in the picture here. We want to be able to take all these capabilities and bring them to more of a different field than the ones that have been highlighted with CSI, surveillance, and hazardous area exploration. In other words, we want to be able to bring this to the autonomous mine. Now, since UAVs themselves are mainly used in a decentralized autonomous way, in other words, the UAV is taking its own decisions based on certain parameters. I want to be able to bring that to autonomous robotics used in an open pit mine. And as the objective of every corporation in this field, we want increased efficiency. We want to make more money, in other words. And the UAV is going to be able to bring that capability to this field. So some mining applications that can be brought by the UAV to the field are, first of all, aerial photography. Now, this picture is taken by Adam Technologies. They took a picture of just a test picture of their work area. So you can see in this picture the 3 trucks. You can see some other equipment that's there. It's actually quite high resolution for something that's flying at a pretty high altitude. If you look at photogrammetry, now photogrammetry is the practice of determining geometric properties from photographs. So we take a number of photographs of the area and we're able to recreate a 3D map or a visualization as seen in this picture here. Now, this is very important if your corporation in the mining sector is looking for heightened command and control, because you send the UAVs, they take pictures at specific coordinates and specific frequency, and we're able to recreate this map. This way, you can have a 3D model and a 3D representation of where all the vehicles, the drills, the LHDs are operating in the area. And then you're able to have that ready for the engineers in order for them to have a big picture of the mine's operation. If we look at the third application, which is facilities inspection, this is a picture taken by Cyber Technologies. It's a company that sent UAVs in order to inspect a Montara oil platform that's been damaged by fire. Now, what the UAVs did was they took live video feed of the area, and as you know, this prevented the engineers from going on board the damaged oil platform and actually getting injured. So then all this live video feed was relayed immediately to the engineers, and they made their plan for cleaning or evacuation, etc. So this is an important application that I've highlighted here that's quite novel in the mining sector, because you send the UAVs and you avoid injury of actual humans when it comes to either inspecting actual facilities or just for maintenance purposes. So having highlighted all these applications, the objective for the project itself is to be able to recreate these in a lab environment as a proof of concept. This has been done already, but I want to be able to recreate it and introduce the viewers that are not accustomed to UAVs to all their applications and how this could be brought to the mining sector for increased efficiency, more money for companies, and heightened command and control. No project is complete without problem formulation. So I've highlighted here the 4 tests that we've conducted for this presentation. So what we have, first of all, is the locate stationary targets. So here, what we've done is we have in the area our three stationary targets, and the objective is for the vehicle, in this case the UAV, to locate these targets, go to that location, and then move on to other targets. At the end, return to its initial position for further instructions. For the second test, locate and follow moving target, what we've done here is we have a vehicle moving around the test area. The objective is for the UAV to locate that vehicle and follow it around. Now, how does this reflect in actual mining applications? Well, for the stationary targets, it could be your drill or your facility, and you want to be able to make sure that it's not damaged. You want to take pictures. For following moving target, it can be represent the haul truck that's going around the open pit mine, and you want to make sure that it's not going off its path, or the error is minimized. This goes back to some of the examples we've done in the homework in this course, where we're trying always to minimize the error. So you can take the data of the UAV following the actual truck and compare it and see if the error is always minimized. So it goes back to the efficiency of the overall autonomous mine. For follow a pre-planned path, this is specific to be able to, for the vehicle to go follow coordinates around the testing area or around your mine in a way that it will cover the whole mine, so that you can take pictures at specific locations and then use that for your mapping or for your photogrammetry. So that's why following a pre-planned path is inserted here. And finally, conduct facilities inspection. What we've done is we mounted the camera on the actual UAV and we tried to inspect a robot in our area. So we took some snapshots, we took some videos, and we'll discuss that a bit later in the presentation. Now, I just want to highlight here the experimental setup that's been used so that the viewers are able to understand how everything fits together. So first of all, we have a 4x4 area which is covered with 16 OptiTrack cameras. These are infrared cameras that are able to pick up on a pattern which is found on the vehicles or on the targets in the area, and this pattern is made of reflective balls. The pattern itself is called a trackable. If you've ever played the video games, you would understand that there's something for the characters. They usually dress in a black suit with all these reflective balls, and they are put in an area similar to this and recorded using these infrared cameras, so that you can pick up on the pattern itself and you can know where the person, or in this case the vehicle, is. Now, all this information picked up by the cameras is rallied to something called an OptiHub, which is then processed by the processing unit. Now, this information is sent wirelessly to the UAV operating in the area, and that's how the feedback is accomplished in our testing arena. Now, you're probably wondering that since there is a processing unit, your control system and everything that's running is centralized there. This is incorrect. The processing unit is simply used to send the information to the Q-Ball X4 or to whatever vehicle is in the area wirelessly, but the computation and the decision-making process is running on the vehicle itself. This is a picture of the equipment used for this experiment. What we have here is in the top left, we see the Q-Ball X4 UAV used for the test. We can see the patterns that are on all four of these quite well. And these are the reflective balls I mentioned before that are picked up by the infrared cameras. And now the mats with the trackables on them represent the targets used for this presentation. Now, if you look at the actual UAV itself, I'm going to give a quick description of it. You can see the trackable there with the reflective balls. You also have this protective layer that's made of these carbon fiber sticks. Now, this is mainly for safety of the operators and of the vehicle itself. So it protects the motors and it protects the CPU assembly that you see in the middle. The actual low-level control, what I mean by low level is maintaining the pitch, angle, yaw angle, and actual Cartesian coordinates is done on the vehicle itself by a number of nonlinear proportional integral derivative controllers. In other words, PID controllers for minimizing the error. So that's how the control is being done. What I've designed for this experiment, which we'll discuss in the next slide, builds upon that. So it's the higher level control that I've used or constructed over the low level PID control. So again, this is how everything fits together within our testing area, and all the information and the data is saved on the processing unit to be able to use in results further. So for the path planning algorithms themselves, for each one we have the different algorithm. They're quite simple, and I won't spend too much time on this. I'll just give you a quick description of how the task has been accomplished autonomously by the vehicle. If we look at the first